Last night, trillions of Big Bang photons slid through you undetected. They were stretched by expansion, so each arrived with less kick. Energy can dodge your instruments while still obeying physics. If you miss it, the trail likely changed shape or path. It might scatter, cool, or redshift beyond your sensor's band. Sometimes it slips behind a horizon your detectors cannot cross. Today we'll trace those routes with crisp, testable pictures. By the end, invisible energy will feel obvious, not spooky. A midnight lab hums softly, a detector chilled near absolute zero. You wait for a click, but the counter stays stubbornly silent. Undetectable energy means it failed to trigger your particular device. You should care because miscounts warp how we read nature's books. Detectors respond only when energy exceeds a threshold set by noise. Interactions must happen, and sometimes the odds are painfully small. Some quanta simply miss because their cross-section is absurdly tiny. Others arrive too softly, sinking beneath your instrument's thermal floor. Geometry can also hide energy behind unreachable horizons in spacetime. Real numbers help anchor this, so here is a scale. About 100 trillion neutrinos cross your body every second. Almost none interact because the weak force barely shakes them. A camera tuned to visible light ignores heat from your phone. Warm radio gear drowns microwaves that a cooled receiver could catch. Tiny test, cover a lamp, then feel the lingering warmth. Your eye reads darkness while your skin reads steady power. Net result, detectability is a partnership between energy, interaction, and instrument. A lonely photon swims through deep space for billions of years. Cosmological redshift means expansion stretches light to longer wavelengths. You should care because stretching reduces each photon's usable energy. As space grows, wave crests drift farther apart, lowering their frequency. Lower frequency means less punch, even though the photon still exists. Nothing rubs or slows it. Geometry alone changes the bookkeeping. When the scale factor doubles, photon energy falls by 1/2. Starlight slides into infrared, then infrared cools into microwaves. Give it longer, and microwaves fade into the radio fog. Here's an anchor number you can picture right now. The cosmic microwave background sits near 2.7 Kelvin. Back then, it glowed around 3000 Kelvin, lighting new atoms. Far ahead, it will chill below a single Kelvin, maybe lower. Rule of thumb, wavelength grows with scale, while energy drops inversely. Bottom line, no energy vanishes locally, but visibility fades globally. Dusty clouds wrap newborn stars, glowing like embers against black space. Dissipation is energy spreading into countless tiny random motions called heat. You care because heat hides detail that your eyes could use. Photons from a hot star strike dust grains and gas. Electrons jiggle, vibrations spread, and the energy smears into phonons. The cloud re-radiates, but now at cooler infrared colors. Each bounce blurs information, while the total energy stays put. Consider Earth's balance, a calm ledger that almost always closes. It absorbs about 240 watts per square meter. It emits nearly the same back out as thermal infrared. Your skin sees none of that glow, but sensors do. Net result, dissipation keeps energy present while erasing useful structure. A star's core collapses, and the shell tears itself apart. Neutrinos are ghostly particles that barely interact with normal matter. They matter because they ferry energy out from impossible depths. Inside the core, frantic collisions make neutrinos by the trillions. Photons bounce and stall, while neutrinos slip through dense layers. With tiny cross-sections, they escape sooner than photons can. Your eyes catch the blast, but miss the real payment. Here is the scale that surprised everyone in 1987. Supernova 1987A released about 10 to the power of 46 joules. Roughly 99% left as neutrinos, not as light. Detectors on Earth saw only a handful of recorded events. Meanwhile, your body sees 100 trillion solar neutrinos each second. You almost never notice because the weak force hardly nudges them. One sentence recap: weakly interacting particles hide energy in plain flight. Space itself ripples like a drum when titans finally collide. Gravitational waves are spacetime ripples that carry genuine energy outward. You should care, because orbits shrink as radiation bleeds away. Accelerated masses shake spacetime, and waves sprint off at light speed. They stretch and squeeze space by a ridiculously tiny fraction. As waves leave, the dance quickens, then ends in a merger. The wave carries energy you can measure through its effect. Here is the benchmark that shocked everyone a decade ago. Event G150,914 radiated about 3 solar masses of energy. That equals roughly 5 times 10 to the 47 joules. LIGO sensed a strain near 1 part in 10 to 21. The mirrors moved about a 300th of a proton's width. Net result, curvature itself ferries energy past stubborn sensors. A dark sphere hangs in space, rimmed by a bright ring. An event horizon is a boundary that light cannot escape. You care because anything crossing it becomes lost to you. Infalling matter heats up and shines madly before the plunge. That light can reach you, but only from outside the line. After crossing, signals cannot return, so your audit ends there. Hawking radiation exists, but for big holes it is feeble. A solar mass hole radiates near 10 to the minus 8 Kelvin. Evaporation takes absurd times, near 10 to the 67 years. Our universe also holds a cosmic horizon from accelerated expansion. Beyond it, light can never reach us, not even eventually. What to remember, horizons hide energy by geometry, not trickery. Gas falls inward, swirling into a glowing disk around gravity's well. Gravitational binding energy is the release from things falling together. It changes what you measure, because motion converts into light. Falling gas speeds up, collides, and shocks into very hot plasma. Turbulence turns ordered motion into heat, then heat becomes radiation. Deep wells can also launch jets from twisted magnetic fields. Gravity's negative potential balances the energy shining into space. Here is a scale you can carry in memory. The Earth-Moon pair holds roughly 4 times 10 to the 28 joules. A collapsing stellar core releases about 10 to the 46 joules. Most of that leaves as neutrinos, not as pretty light. So the picture is, gravity hides energy in careful bookkeeping. A silvered dome shelters a chilled sensor staring into clean darkness. Detectability always has a threshold set by noise, size, and time. You care because shifting that threshold turns missing into measured. Cooling lowers thermal noise, revealing signals that were hiding before. Bigger mirrors gather more photons, raising their chances to register. Longer exposures let randomness average down into something stable. Clever subtraction removes backgrounds, and error bars tighten hard. Here are anchors that show how far this has gone. JWST's mirror spans about 25 square meters in area. It cruises near 40 Kelvin, perfect for faint infrared astronomy. LIGO measures strains near 1 part in 10 to 21. Modern bolometers sense zeptajoule blips, rivaling single-millimeter photons. One-sentence recap: beat noise with design and yesterday's ghosts appear. That opening photon is colder now and unimaginably farther away. We watched it fade by redshift, heat, waves, and horizons. Nothing mystical happened, only bookkeeping and imperfect instruments. If this clicked, you will start seeing hidden energy everywhere. Share this with your space-curious friend and subscribe if helpful.